Okay, so what is elementary cellular automata? Well, uh, it's similar to what we've already seen, which is game of life, except in this case it's one-dimensional. So in game of life, you have a whole grid of cells, and every cell has 8 neighbors that surround it. Well, in this case, we're only working with a single row. So each cell will only have a left and a right neighbor. This is easier to see with an example. Here we have 30 cells. Most of them are dead except for one cell in the middle that's alive. And it will follow a certain set of rules for every cell depending on its left and its right neighbor and itself. And it will produce the next row, which will print under it. We repeat this process on the next row and so on until you get something that kind of looks like this. So what are these rules? Well, this one in particular is called Rule 30. And as you can imagine, there's only a finite combination of these 3 cell patterns. And here they all are, all 8 of them. And if we look at this cell, for example, it's a dead cell and it's got one alive neighbor to the right. So that corresponds with this rule. And you can see that its output for the next row should be 1, meaning it's alive. And if we look, there it is. And so there's all kinds of combinations of these rules from 0 to 255. If you're wondering why this is called Rule 30, well, if you take this string of 1s and 0s, you turn it into a binary number, then you turn it into decimal, there's your answer. And with different rules, different behaviors can show up. You can get really simple behaviors like this diagonal line. You can get more interesting ones like these nested patterns, and you can even get completely chaotic ones like Rule 30, which is interesting because on one side of the triangle it has a very simple repeating pattern, and on the other side it's completely random. Some of these rules are even Turing complete. Okay, I'm gonna do. This book is called A New Kind of Science by Stephen Wolfram, and it's the first book that came out about this kind of cellular automata.
In American English, however, it is normally said as automata.
And it expands a lot on these basic ideas. It's only $20 on Amazon, and you could fucking kill someone with it. But it's got pretty wide margins and lots of pretty pictures. So you could just flip through here, like, you could say, oh, this looks kind of cool, and then you could try to read about it and implement it yourself. I do have to say, though, that outside of information about cellular automata and its behaviors, this book is filled with all kinds of bold claims and repeated statements, which has earned it its fair share of controversial reviews. If you can get through all of that, this book is still worth getting. Okay, so I'm opening up a blank processing sketch. I also have opened the Rule 30 Wikipedia. This has all of the 8 rules for it on here, and I think it's just a really cool one of these. So we're going to start with these rules, and then we're going to expand it to work with any of the elementary cellular automata. First of all, to represent each row, I'm thinking an array of Boolean values is going to be just fine. If it's true, that means it's alive, which also means it's a 1. If it's false, that means it's dead, which is white. And that's a 0 up here. So let's do that real quick. Let's make our setup method right here. We're going to make this like 600 by 600, whatever. And we also need to know how big each cell is going to be. If we make each cell like 10 pixels, for example, then if the width of this page is 600 pixels, then there's going to be 60 cells in this row. So now we know the size of this, and that will be width divided by whatever cell size we chose. Now we can give it an initial condition. The initial condition could be anything, but in all of these examples, it's all of the dead cells with one alive cell in the middle. So let's do it like that. The way I'm going to do this is I'm going to make every cell turned off by default, and if it's in the middle, we're going to turn it on. And now let's draw this to the screen just to see, make sure everything's working. So we're going to use the same loop, go through each of the cells. If it's alive, then we want the fill color to be black. Otherwise, then we want it to be white. So for each cell in this array, we're going to draw a rectangle on the screen. And what does a rectangle need? It needs an X and a Y. The X is going to be the position in the array times the size, right? And we need some kind of variable for the Y, because we're going to start on the first row, and then we're going to increment the Y variable so that we can print that row on the next line. So let's make it up at the top. Y times 0, or times size. The width is going to be size, the height is going to be size, and let's just see if this worked. And yes, it worked. But I want this to be no stroke. Okay, cool. And now you can see if we increment this Y variable. By the way, if you haven't used processing before, the draw loop runs over and over every frame. And that's kind of how it's going to print to the screen. Of course, now all we need to do is update each row according to these rules. So I'm actually going to make a different function for this just for clarity. We could put it in the draw loop, but whatever. We're going to need some kind of temporary row variable. We need to store all of the new cells, what the cells are going to become in the next row, in their own row, because we don't want to update them one at a time. We want to update them all at the same time. If we update them one at a time, then if I change this cell, then the cell next to it has its neighbors changed and it fucks everything up. So let's make a next row variable like this, and it's going to be the same length as row. And what do we need to do? Well, we need to go through every cell and check it against its left and its right neighbor and itself to make these patterns of 3 numbers. So the way I'm going to do that is I'm going to have some local variables. We're going to have one called the center. That's going to be pretty obvious. It's just whatever cell we're iterating on. We're going to have one for the right. And we're going to have one for the left. Now you might be thinking, well, what if the cell doesn't have a left cell or a right cell? For example, this one doesn't have a left cell and this one doesn't have a right cell. In this case, I'm going to make them wrap around. So if it's over here, its left neighbor is going to be the one all the way on the right, and if it's over here, its right neighbor is going to be all the way on the left. Great, so now we have this left, center, right cell, and we can actually just check with 8 different if conditions to see if it matches each one of these patterns and what to output. You could make this some really beautiful nested if-else statement kind of thing, but I'm just going to do it like this. So I wrote all these conditions and they match exactly these conditions, and I'm just curious if I need anything else. Oh yes, well, so I put all of these cells into the next row. When I'm all done with this loop, well then I want to update the row. So row equals next row. And let's just see, if I put update before this display thing, is it gonna do it? No, of course not. Oh yes, okay. Well, this is just a funny way that I did it. So, okay. Okay, I think this will work now. Let's see. Hell yeah. So now I'm going to make this smaller. Let's see if it does the thing. Boom. Okay, so you might remember from earlier that each of these rules gets its name by turning this set of rules into a decimal number. Like turning this into 30 gives you rule 30, and you can do this with any of the sets of rules. There's 256 of them. So I want to do the reverse process. I want to have something in here called rule, and I can make it 30, and it's going to give me what we have. But if I change it and make it 50 or something, I want it to be different. So the way we're going to do that is we're going to convert this rule into a Boolean array, much like our rows array. So I guess we could call that rules. And how big is it going to be? It's going to be 8, just like the examples. And then later, when we go actually checking each of these conditions, we're just going to, instead of making it manually 0 or 1, false or true, we're just going to refer to this rules array. And if we run it right now, because we made an empty array, I think it's just going to be white. Yeah, there we go. So what do we need to do? We need to first of all turn rule into binary. So in processing, we have something called binary, and this gets the job done. If we print this, you'll see we get a very long binary number. We only need the last 8 digits. These are all leading zeros. And this outputs as a string, by the way. So we could make, for example, a rule string. I know we're getting a lot of variables, but this is going to make things easier. And then we can make this equal to the substring of itself. Substring is just, as it suggests, part of a string. And where is the substring going to start? It's going to start 8 from the end. So rulestring.length minus 8. I think that'll look right, but let's just print it to see. And there we go. Now we have 8 of them. So now that we have a binary number, we can fill up this rules array correctly. We're going to just iterate through every character in this string. If the character is a 1, that means we want to add true right there in our rules array. Otherwise, this is going to be false. And I think because we already edited this is going to be all we need. And boom, there's rule 30. And except this time it's actually determined by this variable at the top. So if I make this 50 or something, ooh, it's different. If I make this, let's see, 110, you get a different one.